I would like to show you the features of the FVA Workbench today. We're going to have a look at some slides in the beginning, and afterwards, I would like to jump right into the software and show them in the software. The FVA Workbench is, to our knowledge, the most reliable tool on the market, and it is the most efficient tool on the market. This is due to the fact that the basis of the FVA Workbench is the research from the Research Association for Drive Technology, FVA. With its easy to interpret output and result data, it makes sure that you will have the most efficient tool and the most easy tool to use for your products. With the FVA Workbench, we are reacting on market trends that we see in the market at the moment. With a complete redesign of our calculations, we managed to cut the calculation time by up to 80%. And that is comparing to the FVA Workbench 6.1, so the latest version on the market. And with that, we are convinced that the FVA Workbench is really the most efficient tool on the market. But we're also realizing that it is especially important to work across departments and across tools. And therefore, we enlarged the calculation scope, and we managed to add additional tools and interfaces to our software. We're going to have a look at that later on. With a reliable digital twin, it is now possible to calculate with the FVA Workbench plastic gears. I'm going to show some pictures to that later on. Therefore, we're going to use the Abacus calculation kernel, the finite element tool Abacus, for a nonlinear plastic deformation. Also, you could include additional masses and additional centrifugal forces. And like it is shown in the picture on the right-hand side, you now can also include wheel bodies into the system analysis and make sure that you have those deflection also considered. With the calculation scope, we're going for as detailed as possible and as fast as possible for the most reliable experience for you. With your gear design, you're going through a whole array of tasks for you to calculate, and the FVA Workbench provides you with a broad variety of calculations for static and quasi-static analysis. Therefore, we teamed up with AVL and managed to have a common interface based on the reusable engineering exchange standard REX that allows us to exchange data and make sure that your data is flowing freely through the calculation process, from the design and the concept phase to the time domain calculation within AVL Excite for eAxle. Now I would like to show you some calculations directly in our software, and therefore I'd like to change into the software. At first, I would like to start with a new standard calculation feature. As you might have heard, the ISO TR 15144 for micropitting load capacity has been added to the ISO 6336 as part 22. And the changes made there, we also included into our calculation range. Here, in the calculations load capacity, ISO 6336. You find in the tab ISO the calculation of micropittings. We could activate that by clicking the button there, and here you see additional additional features to change and to apply to your model directly. I would like to let them as a default, and we could start the calculation. For that calculation, please make sure, and I would like to draw your attention to the phase load factor. I made it as a fixed input value. I choose 1.2. For the system analysis, we're later on going to change it to method B, determine it by the system calculation. As a report template, I'm going to choose the cylindrical gear stage, load capacity, and here we added a whole new array of report templates, and here you could find the ISO 6336 part 22. I select that report template and open it in my browser. And here we can see a whole array of results, and especially interesting is the diagram at the bottom. Here we can see that at point A in the mesh, that the safety factor against micropitting is below 1, so we are expected to find micropittings in the foot root area. At point C, we are experiencing a safety factor of 2.3, so it might be the case that we'll only experience the micropittings in the foot root area, not on the whole flank. If you would like to analyze how to improve the safety for micropittings, you could change the diagram here with those drop-down buttons. For example, we could have a look at the flash temperature, and then we realize that the flash temperature in the beginning of the mesh is quite high, with about 200 degrees. Of course, you could change both plots for any relevant data across the mesh. For example, not fixed to the safety factor, but also, for example, the sliding speeds or any relevant data on that subject. We also included the calculation into our system calculation, and therefore I'm changing back the phase load factor calculation and let it determine by the system deflections. In order to activate the calculation, you need to have the load distribution analytical activated, and then choose the temperature distribution and micropitting calculation. Now I'm changing the report template to our system report. In the system report, we have most of our results, like, for example, the result in for the micropittings. And if we're scrolling down into the output for the gear stage, and in the lower areas, we can find the safety against micropittings. And here for the calculation within the system calculation, we can see that by looking closely onto the gear, that we have only a small area where we have a safety against micropittings below 1, and a wider area where the safety values are above 1. even though it is not much. We could have a look at the second stage as well. In the lower area below the pressure distribution, there we have the second diagram for the safety of the micropaddings as well. Okay. Besides the new calculations, we also added some new diagrams in our report. For example, we have a new bending line. You're probably familiar with our old bending line diagram, the 2D diagram, where the bending line is displayed in B and W direction. This is not very intuitive, and for most users it might be more intuitive to have it as a 3D diagram. And this is why we have added the 3D diagram, and here you could also increase the scaling factor. So you could show it as in a higher scale and make sure that you see all the deflection in your shaft. Additionally, you could add or hide the bearings. You could add or hide the transparency. And here you could also find locations that are specific for the diagram, for example, an ISO diagram, or if you would like to have a look from the side and compare it with the bending line in the old format. You will find such lists in many of our 3D diagrams now. This helps you to navigate to certain positions in the diagram and make sure that you have them, can read out the data as reliable as possible. Within our gear section, we also added a new diagram, which is especially interesting for manufacturing the gears. That's the K-chart diagram. Here you could see the proposed area where you could expect your modification to be located. The width of this colored area is decided by the quality of your gear. If you change the quality, you could expect that the colored area is going to be more narrow or even wider if you're choosing a rougher geometry, a rougher quality. We also added additional interfaces. For example, one request was to add a DXF export. And here on the automation tab, you can find global scripts. Those are examples that we are providing for you. And you could choose, for example, the contour of one gear as a DXF file. I'm double clicking it, and you could see that we're getting a selection window. Here I could select one gear, and I'm clicking OK. Then it asks me for the resolution, and I'm choosing coarse resolution because for me this is going to be fine enough. To display the gear geometry, I would like to show it in FreeCAD. I'm drawing the output. You could see the date. That was the export from. Right now, it takes a couple of seconds, and we will have our whole gear in CAD as the DXF file. And as you can see, even though I choose to have it coarse, this is rather fine, so rather fine discretization, especially in the foot root area. And even though I have a quite fast computer, if I'm choosing the fine resolution, it might struggle with such a resolution. The DXF file is exported, as I said, as a script. You could access that script via the scripting interface and use the standard interface we're delivering with the FVA-Workbench. It is not, you can use it not only for gears, but also for tables. If you would like to have a gear stamp as a DXF file or anything else. And besides the DXF interface, we're also delivering a interface to Excel as well, and where you could access an Excel file, make it very easy for you to write the data that you generate in the FVA-Workbench in a standardized Excel sheet, for example. In this gearbox, I deliberately choose SKF bearings, and this is because I wanted to show you that we also included the SKF calculation service. In order to use the SKF calculation service, you would need to register at SKF. It's very easy. You can access our preference window, select the SKF calculation service, and here you could enter your SKF username or your password. If you don't have an account at SKF, you just click here and we redirect you to SKF, to the SKF My SKF service, and there you could register for an account and use the service. In order to tell the FVA-Workbench that you would like to use the SKF service, please go to the gear system, and under control parameters, you can find the button Use SKF Calculation Service for SKF bearings. And by selecting that, we're now sending the SKF bearing with the load data to the SKF server and let the bearing calculation be done by SKF. I'm clicking the system calculation. And I would like to change the report for the rolling bearing SKF calculation service template. And here you can see that in contrast to the report before, we don't display the inner geometry. This is because SKF will not provide us with the results of the inner geometry. However, on the SKF service, the inner geometry is considered. And you can find this as a note here in the forces on rolling elements diagram. And also, we're going to compare it with our solution in just a moment. You can find it on other parts of the calculation as well. For example, the attributes, they change quite a bit in the attribute description, and there it says, okay, that's calculated from the SKF service. I'm deselecting the SKF calculation service and run the calculation as well with our internal module. And if I use the compare functionality of the FVA-Workbench, and I scroll down to the forces, the first thing that you see is that the signs do not match. You could also see it here in the forces and rolling elements diagram. And I would like to draw your attention to the coordinate system. For tapered roller bearings and bearings where you only have an actual force absorption in one direction, it is crucial to take a look at the coordinate system, because that might be confusing for the on first sight. However, if we are comparing the second bearing, the coordinate system align, and it makes it more easy for us to compare the forces. For this bearing, we have a radial force in x direction of about 3,000 Newton, 3 kilonewton, and the difference between the SKF solution and our internal calculation of about 50 Newton. So in conclusion, we can advise you to use the SKF calculation service if you're using SKF bearings. However, the internal estimation of the inner geometry is just as fine, and the differences are not that huge. Now I would like to add a wheel body. Therefore, I'm navigating to the intermediate shaft. This is the middle shaft here. And there I already added the component cylindrical gear wheel body. And here I can change it from massive to elastic from CAD file. You also have the opportunity to use it from a point table. Here you could enter points radially and with the width direction. However, I find it more convenient to use the CAD file. Then I'm going to import it from my hard drive. I select the unit system that I used for the design of that wheel body. And you could see that within the 3D model, I now have my desired wheel body. I can see that the position of the wheel body is correct. This is by design, because I used the same coordinate system for designing the wheel body as we are using in the FVA-Workbench. If you're using another coordinate system, please make sure to perform the positioning at first. So I'm now running the internal FEM measure. And the first step is to select the inner axis. Therefore, I'm clicking on the inner bore. And what you could see here is that we cut the outer diameter to a certain diameter. And if the wheel body is too slim at the outer rim, then we are also adding material. This makes sure that we have no gap between the analytical teeth and the wheel body. By clicking OK, the FVA-Workbench opens the internal measure. And here I would like to perform the quality check after the volume meshing. I'm using the standards, the default values for the mesh. and create the volume mesh. And with the element quality checker, we could see that at the moment we have no critical elements and no unqualified elements. However, if I change the limit for critical elements, we could see that we have slightly distorted elements here, and in the beginning of our bores between the bores. However, they are not as distorted as it would to such a point that it would be critical. So I could accept that. Now the FVA Workbench runs the measure a second time. The first mesh is going to be used for the analytical solution for our system analysis. The second mesh you could see has a thinner rim to the gears as our first mesh. You could see that it ends here at the right below the reference circle. This wheel body here is going to be used for the finite element analysis with Stirak. I'm also going to use the default values for our FEM measure. And now it changes to the second mesh. So fourth step, we already checked that one. The third step, that the FEM mesh quality has been inspected. Now we would need to select the nodes, and we could see that all the nodes on the inner and the outer diameter have been selected correctly. And now we have to perform the fifth step, which is calculating the stiffness. The stiffness calculation takes a little while, but the nice thing about this is that the stiffness calculation only has to be performed once. Whenever you have the stiffness calculation ready, it is not going to be calculated over and over again. We're going to store the stiffness in the background in the model and reuse it as long as it is valid. You can make this stiffness calculation invalid by changing the position of the gear or changing the position of the coupling nodes. This also includes the gear data. Whenever you're changing the reference diameter, of course, you have to change also the diameter where we're cutting the wheel body, and therefore you have to remesh the wheel body, again snap the coupling nodes and calculate the stiffness. But as we have seen, this can be done within 5 minutes, and now we're good to go with a system calculation. Now I would like to use the compare feature again. Here, I'm now naming my model snapshots, calling this with body, wheel body, and this is the analytical wheel body. And I'm using the compare tool. Need to change also the report template to make sure that we could have a look at the load distribution. What we are expecting from such a wheel body, you could see that the rim on the wheel body is quite narrow. It is only half the width of the whole gear width. And I would expect that we have an increase in load distribution. Therefore, we are going to select the input stage and scroll down to the load distribution. And the first indication is we have a different displacement. And here at the load distribution, we could see that our load distribution factor has changed from 109 to 111. If you're decreasing the thickness of the rim, you could expect that this effect will increase. And by thinning the rim here, you could also increase this effect. Now it might be beneficial to compare that with the deformation calculation. Therefore, I'm rerunning the calculation to save a little bit of time, deactivating the load distribution calculation, the 3D load distribution calculation. And then we could have a look at the deformation of the wheel body. Therefore, I'm hiding all the other components. And I use the show gear deformation and show FEM component deformation button here in this window. Because it deforms quite drastically, I'm decreasing the scaling factor. You could realize that, or you could see that the wheel body increases in size. This is due to the fact that the load is applied around the circumference of the gear and in tangential direction. And this leads with a sufficient scaling factor to an increase in the volume of the gear, but this is only a visual effect. There's nothing to do with the real result. We now could see that here in the area where our mesh is located, we are having an increase in deformation. Deformation is shown as a red color, and also slightly skewed. And this can be, we can see that this is resulting from the distribution of the torque on the gear. We're going to the intermediate shaft and to the shear force distribution, that the shear force the torque here is increasing quite dramatic with the U axis. So on the right hand side we have maximum torque, where on the left hand side there's basically no torque. And this is what we could see here as well in the deformation window. Okay, we have a couple of other features as well. As a new component that you could add, there is the mass point. For example, I'm going to show the whole gearbox. For example, if you would like to model the motor which is attached to this shaft, You could do that with a mass point. There you could add a mass of the component. Also, you could add a moment of inertia, and especially relevant for dynamic analysis, you could also add an eccentricity. And with that, you will have an additional force in radial direction. And this is visible in the eigenvalue analysis. So, sorry, I forgot one thing I would like to show you. So for all the calculations that I have shown, they're quite advanced. They're very detailed. However, the FVA-Workbench is also capable of designing gears from the scratch, but then you most likely have the problem that the designer would not want to deal with gear modifications, but they would like to focus on the bearing selection. And in helping, we wanted to help them, and therefore we added another button that we could consider the tooth loads as a single force. That helps you to design the bearings in such a way that the deformation of the gear is not taken into consideration over the width of the gear, but it is only applied as one singular force. So the resulting forces on the bearing are comparable to those that you would have in an optimal modified gearing situation. We could run the system analysis, and now it informs me that I have forgot to add a mass to our mass point. Not going to do that and delete it again. So I'm rerunning the system calculation. What I wanted to show you is that I cannot I need to remove the wheel body, but it is going to, if I have what I wanted to show you, if I have the load distribution or any other local load carrying capacity analysis activated, you will get an error message that is informing you that the combination of a local load carrying capacity together with a singular force as a gear tooth force is not possible. That does not make any sense. Let's have a look at the results. And if we have a look at the shafts, here at the shear force distribution, you could see that the forces are applied in the middle of the gear width. And same applies for the bending moment and the torque and torsion. As an effect of that, you will not find any output of the load distribution in the report, and also, as I mentioned, there will not be any output of local load carrying capacity load analysis. However, this makes it very easy for you to analyze your bearings and design your shafts. And with that, I would like to return to my slides. As I mentioned in the beginning, we also included the plastic gear calculations that were found in FVA 892. The objective was to have a fast and reliable calculation tool that can take into consideration the nonlinear material behavior of plastic gears, and it follows the same principle that I have shown you with the wheel body. We just add another solver that we're going to use Abacus, but for you as a user, it feels as it would be in the FVA-Workbench. So you would have an automatic mesh generation of the gears. There we're using the Stirak as a meshing tool. Then you have to position the plastic gear. And we are generating the Abacus model internally. You don't have to use Abacus for that. We send it to Abacus, or you could transfer it to a calculation node and solve it. After you have the Abacus solution and the resulting file, you could return with the solution to the FVA-Workbench and use the reporting mechanism in the FVA-Workbench to evaluate the results. So to summarize, you have a reliable process even for non-FEM experts that takes the nonlinear material behavior into consideration. Also, I hope that you have seen that we are faster than before. We did some performance measurements, and for some calculations, it saves up to 80% of simulation time. This is due to the fact that we rigorously redesigned all our calculations. We did parallelization of time-intensive calculations, and by all that, we had no compromise for calculation quality. So you will still have the same results and the same quality in results, but you have it even faster. For the last slide, I would like to show you the new seminars, the upcoming seminars that we would like to, where we would like to draw your attention to the new features of the FVA-Workbench. I've shown today a couple of them. However, we have even more. For example, we would like to show you the calculation of the transmission losses. We will have a web seminar together with AVL, where we're going to show the interface between the FVA-Workbench and AVL Excite. Also, we would like to have a deep dive on the wheel body design on the 22nd, and on the 23rd, we're going to show you the calculation of the plastic gears. So at last, I would like to invite you to have a look at our social media platform. We are especially active on LinkedIn. And if you would like to be up to date to all our information, I would like to invite you to our newsletter. With that, I would ask you if you have any questions, and would invite you to post them in the questions board. There we have one. This question is regarding whether the FVA-Workbench has all relevant tolerances, including the tip diameter tolerance, tooth thickness tolerances. You could go to the tolerance specifications. The tooth thickness can be tolerated. Also, there's a tip clearance tolerance. However, there are no tool tolerances yet, but we are planning on including them as well. For the moment, you have to add them manually and change the height of the tool manually. Are there any additional questions? I see none. I would like to thank you very much for your time. And oh, there are two coming. What about bevel gears? Not sure what you're referring to. Of course, for the bevel gears, we have a wheel body as well. This was included at the FVA-Workbench 6.1. You could use that as well for your analysis. At the bevel gear front are, in addition to that, no significant new features. Nothing in what comes near to that what is shown. The changes in bevel gears are mostly bug fixes. Okay, if there are any further questions, I would like to thank you for your attention, for your time that you took to have a look at the new features. If you have any further questions, please let me know. You could reach me per mail or via social media. And I would be happy to hear from you soon. Have a good day. Bye-bye.